All right, guys, moving on to the long problem from Chapter 7, Test Review. So this one right here, we're going to be looking at how to find the probability of a proportion using all of these wonderful, beautiful steps that are scaffolded out so that way it's a step-by-step process. So let's go ahead and take a gander. So the first part says, a potato chip producer and its main supplier agree that the shipment of potatoes must meet certain quality standards. If the producer finds convincing evidence that more than 8% of the potatoes in the entire shipment have blemishes, the truck will be sent away to get another load of potatoes. Otherwise, the entire truckload of potatoes will be used to make potato chips. To make the decision, a supervisor will inspect a random sample of potatoes from the shipment. Suppose the proportion of blemished potatoes in the entire shipment is P equals 0.08, and the supervisor selects N equals 500 potatoes for inspection. What is the probability that at least 11% of the potatoes in the sample are blemished? So from all of this, a couple of key pieces of information. We know that P equals 0.08, so 8%. We know that the sample size is 500. And we also know that we are trying to find the probability that X is at least 11%. So at least means greater than or equal to 0.11. That is our goal. This is what we're trying to find. Okay. So let's go ahead and start with number one. So number one says to calculate the mean and the standard deviation of the sampling distribution of P hat. So our mean for our sample proportion, and we know that this is a proportion problem because we have percents. So percent equals proportion. Okay, so for the mean, it's going to be 0.08. That's our sample mean for the proportion. The standard deviation for the sampling distribution is going to be equal to the square root of P times 1 minus P divided by N. We're going to be using that formula. And in that formula, we know that P is 0.08 times 1 minus 0.08. Oh, got to make sure it stays underneath the square root. Divided by our sample size of 500. We type that into the calculator and we get, y'all can pause if y'all want to go ahead and type this in the calculator just to stay with me. I already did these calculations and I found that that is 0.012. Now, if you were to go off further and do more numbers for the standard deviation, you would actually get a more exact, a more precise answer. And it's up to you how many digits you want to round it to whenever it comes to the paper portion of the test. Because in the very end, if you were to not use the exact same standard deviation that I used, your final answer would be slightly off, which would give us slightly different answers. But if you can show me where all your numbers come from, you're likely going to still get all the points. And your answer will be more precise than mine. So that's exciting. On number two, it says justify the sampling distribution is approximately normal. And then it gives you a little hint. It says check both conditions. Okay. So because this is a proportion problem, that means we're going to be looking at the large counts condition. So we're going to figure out, is n times p greater than or equal to 10? And is n times 1 minus p greater than or equal to 10? It has to meet both of these conditions. Now, if it doesn't meet these conditions, you get to just move on to the next problem, because if it's not normal, it's going to be skewed, which means it's going to be biased. Now, that's not going to happen on your test. It will definitely work, but you have to show that it works. So we're going to look at n times p. So that's going to be 500 times 0.08. And we want to know, is that greater than or equal to 10? And, oh no, I did not actually solve this beforehand. So we're going to solve this together real quick. So 500 times 0.08 is 40. and 40 is indeed greater than or equal to 10. So then we're going to do the other one, 500 times 1 minus 0.08. And that would give us 460. And 460 is indeed greater than or equal to 10. Okay, so we would say it works by the large counts condition. Okay, so the next thing that it does is, because it's a normal distribution, we get to continue on. And it says shade in the area that you're looking for. So here we have our normal distribution, our bell-shaped curve. In the middle of our normal distribution, we're going to have the mean, 0.08. Now we're going to have to go back to figuring out what the problem wants from us. And it wants to know the probability that it's greater than or equal to 11%. So somewhere over here, there's going to be a 0.11, and we're going to shade to the right because we are looking for the probability that x is greater than or equal to 0.11. Moving on, it says to calculate the z-value. So we know that x is the value that we're looking for, so 0.11. We know that the mean is 0.08, and the standard deviation, those are supposed to be p-hats. The standard deviation is 0.012. So I'm going to do z equals x minus the mean divided by the standard deviation. So this is going to be 0.11 minus 0.08, all divided by 0.012. If we were to solve that out, you would get to 0.5. Next up, it says use table A to find the z-score. So we're going to look for the probability that z is less than 2.5. Now, the reason why I say that it's less than is because in table A, it only shows us the shaded area to the left. It only shows us less than. So we're going to go to 2.5. The next number would be a 0. So 2.50 would give me 0.9938. 0.9938. Now, that is the shaded area to the left. So on number 6, it says, what is the numerical mathematical answer? And that is simply checking your shading. So if table A shows you the shaded area to the left, but we want the shaded area to the right, we have to do one more step. And that is remembering that this entire curve's area equals 1. So if the entire curve is 1 and this shaded area is 0.9938, to find the other area, we're going to have to do 1 minus that number, and we will get 0.0062. And that will be our probability. That's our final answer. Okay, in the next video, we will discuss sampling distributions of a sample.